So especially after this last session, we should thank the organizers for putting together a conference like this, like insisting in the discussion of these topics. And actually, maybe I would invite all of us here in the audience to keep this in mind for the next conference that we'll organize. No, maybe it's a good idea to keep a spot for discussing this kind of topics. I think it's quite useful and has a lot of impact discussing this in the conferences. So, okay. So what I want to talk about is joint measurability. And so I'll present some recent results I have with different collaborators. So the only one here is Marcelo, here. So what I want to convince you of is that actually joint measurability plays a central role in quantum measurement theory, but also it's a nice property for us to have in mind because it's important also for general operator theory. So I'll start. Where is the choo-choo? So okay. So I'll start presenting joint measurability and interpreting it in two different ways. And then these will lead us to the discussion of simulation of quantum measurements. And then we'll talk about model uniqueness. And then a generalization of Birkhoff-von Neumann's theorem. So we start with the very operational definition, which is joint measurability. And then we'll move towards pure mathematics, which is something I really like. Okay, so just as entanglement is the most striking non-classical feature of quantum theory in terms of quantum states, in terms of quantum measurements, incompatibility is the most striking feature of the theory. So these are the two main notions in each of these classes of objects. So there are different notions of measurement compatibility. So we can talk about commutativity, about non-disturbance, about joint measurability, which is what we'll focus here today. But there's also coexistence and different notions of it, right? But then from now on, when I talk about compatibility or incompatibility of measurements, I'll be referring to joint measurability. So what's that? So imagine, so let's picture quantum measurements as boxes, right? So here I have a box A and B, and then we're throwing in a sum state row, okay? And then on the other side, we're left with some outcome that, of course, appears according to Born rule. So on the other side, imagine that we're implementing only one measurement, M, that gives rise to a pair of outcomes, right? So we'll say that A and B, they are jointly measurable if I can understand them as only one measurement, such that the statistics of this pair, they allow us to recover the statistics of each of these outcomes here. So writing this mathematically, we'll say that A and B are jointly measurable if there is this modern measurement, here M, such that for any state row that we're measuring, we can marginalize the statistics of M, and with this we recover the statistics of A and of B, okay? But then since we want to recover this for every quantum state row, actually we can get rid of row in the trace, and then we reach an equation involving only the measurement elements here, M and B and A and B, okay? So as you can see, this is a very operational definition, right? So another way, so this is how we visualize joint measurability from the point of view of simultaneity, right? We're simultaneously addressing an outcome for both of these two measurements here. And of course, we can generalize this for more than two measurements, for any set of measurements. Another way of interpreting joint measurability is okay. Okay, so of course. So a very visual way of displaying this modern measurement M is arranging its elements in a table like this. So we can see the marginalization happening as summing over the rows and summing over the columns, right? So if we fix the first label and we sum over the others, we're summing over the line, and here we should obtain the elements of the first measurement, and summing over the columns, we should recover the elements of the second measurement. So another way of interpreting joint measurability is as a simulation protocol. So imagine that I have again this, this is hard, no? So imagine that I have again these two measurements A and B. And now what I'll do, I'll implement a single measurement M that will lead me to only one outcome. And then I'll post-process this outcome according to the measurement that I want to recover at either A or B. And then from this post-processing, I'll be able to address one outcome for each. And if the statistics in both of the situations are the same, then I'll say that A and B are jointly measurable. So mathematically, we just write this as something like this. There is this M tilde, which I also call a modern measurement, and a post-processing map Q, such that for any state row, I can implement M, post-process it, and then recover the corresponding outcomes of the corresponding measurements. But again, since I want this to hold for any state, I'll get rid of the trace against the state, and I'll reach just these two equalities involving the measurement elements and the post-processing. Okay? So the existence of an M, which is the first situation, and the existence of M tilde, which is the second, they are two equivalent things, right? So these two are really two ways of interpreting the same thing, which is joint measurability. So that's why I won't make a difference about names about this. I'll name these two objects here as modern measurements. So the fact that we understand the joint measurability as a simulation protocol allows us for a very natural generalization of it, right? So actually, joint measurability, according to this simulation interpretation, is the simplest form of measurement simulation because it involves only a single simulator, and we don't put any constraints on it. We just ask there exists this POVM. It doesn't have to suffice any conditions. So a very natural generalization of it is just to increase the number of simulators, right? So what we'll obtain in this situation, we have here a set of measurements running from A1 to AR. And now what I'll have, it's a set of simulators, M1 to Mn. So for this to make sense, we want that R is larger than N, right? So we want to simulate a lot of measurements using fewer measurements. So what I'll do if I want to recover the jth measurement here, I'll just flip a coin, which is represented by new here. And then this coin will tell me which simulator I should implement. I'll implement this measurement, obtain this outcome M here, and then post-process it according to the measurement I want to recover, according to the simulator I implemented, and according to the outcome I obtained from the simulator, right? And then what I want is that these statistics here takes me to some AJ that has the same, which has the same statistics of the jth measurement here, AJ. So we write this via this equation here, which is just describing this situation. So this is what we propose in this work here, and then for this part, it's all of what I'm saying right now, from now on, is on this paper here. So as an example, consider these four measurements here, sigma x, sigma y, sigma z, and the combination of the three of them, okay? And consider the depolarization map. So the depolarization map, it takes an operator, right, and then mix it with identity. So if you do this for every element of every measurement of this set here, we obtain noisy measurements, and then what we'll see is that when this parameter here, t here, is 1, I have exactly this set here, right? So if t starts to decrease, so we'll move here from 1 to 0. As t is decreasing, we are considering more noise in our system. So here at 1, we have exactly this set here of these four measurements. We start adding noise, and at some point here, this set becomes 3 POVM simulable, meaning that I can implement any of these four measurements through only 3 measurements, 3 simulators. And this is very nice because actually this happens before any 2 of these 4 measurements are compatible. Up until this point here, any pair of these 4 measurements, they are incompatible. They are not jointly measurable. So this really says that actually considering more simulators, we have something strictly different, strictly more powerful than considering only joint measurability, which is simulation via only one simulator. Okay? And then the more noise we add, we have like better properties, or simpler properties of simulation. So at this point, I can simulate these 4 measurements by 2 POVMs, and it's also the point where each pair of them becomes compatible. So considering even more noise, we have that any 3 measurements of these 4 are compatible until we reach this point well, the whole set can be simulated by one POVM, which is to say that the set is jointly measurable. Okay. Do we have any questions about this part? Okay. So we can move to a second generalization, which is imposing qualitative restrictions on the set of simulators. And with this, we'll find some specific forms of simulability. So yesterday, Michal presented to us results on projective simulabilities, right? Which is a simulation using only projective measurements. So this is one of these other forms of simulability that I mentioned here. So what happens is that actually even these other forms of simulation can also be described in terms of joint measurability. So for instance, if we talk about simulation by k outcome POVMs, we restrict our simulators to have only k, at most k, non-zero outcomes, non-zero elements. What we can do, we can describe the set of POVMs that are simulable by k outcome POVMs as the set that exactly the POVMs that admit this trivial POVM p times identity here, which is like just a trivial measurement where all elements are proportional to the identity. So this pair is always jointly measurable. But now if it admits a modern measurement with some sparsity condition, so this turns out to be equivalent to k outcome simulability. Okay? So I think this is very nice, actually. So we're talking about a different form of simulability, but we still phrase it in terms of joint measurability, imposing conditions on the model. So I think it's nice. The other thing, the other situation, which is what Miho presented yesterday, well, not this result, but this case, this projective simulability, is that in dimension 2 here, a POVM is simulable by projective POVMs if and only if this POVM is jointly measurable with its block antipodal measurement. So we have here the tetrahedral measurement for qubits, right? So it's exactly the qubit measurement that whose block vectors they form a regular tetrahedron. And here in green, we have the block antipodal of it. We obtain this block antipodal measurement by flipping the block vectors of the measurement. So we see that actually these two measurements, they become jointly measurable if and only if at exactly the same noise parameter that this tetrahedron can be simulated by these projective measurements represented by here these blue arrows, right? So again, it's another form of simulability that is phrased in terms of joint measurability. So with this, I hope I could convince you that actually joint measurability is a key concept for talking about POVM simulation. So since we're talking about simulating POVMs, we might want to define an optimal way of simulating some set of POVMs, right? But then if we want to talk this, we need to answer a prior question, which is, when is the simulation unique? So we're dealing with this duality, right, of existence and uniqueness. So we'll focus more on this question right now. And actually, my plan was to describe a bit of this work here, but I think it would be too much dense. You can thank Lausia for this. She convinced me to not speak about this thing. But just to say that actually what we find, well, what we study in this paper here is the relations between the position of the set of measurements in the jointly measurable set and the uniqueness and extremality or boundary conditions on the modern measurement. So we have that extremality of the set is sufficient to guarantee uniqueness of the model, but is not necessary. And on the other hand, to lie on the boundary of the set is necessary, but is not sufficient. Okay? So I won't say much about this. But okay, let's take a very particular case study on the plurality of modern measurements. So perhaps the simplest example of a pair of POVMs that admit multiple modern measurements is this very lame pair here. A is equal to B, equal to identity over M for all of the elements. So for practical purposes, it doesn't make any sense to study this, right? Because it's really an awful POVM, like not quantum at all. But if we are trying to understand one property, which in this case is a modern uniqueness, a uniqueness of the modern measurement, maybe it makes sense to start from the most simple example, right? So what we see is that a modern measurement for this pair will satisfy something like this. We can place the elements of this model in a table, and all of the rows and all of the columns will be summing to identity over M. because all of the elements of these two POVMs are identity over n. So if we rescale this table, multiplying everything by n, we find this, right? We have just identity here, and then this m price is just the previous m multiplied by n. And we have this object here. And then if we look at this a bit more carefully with a bit of creativity, actually we can see that this is some kind of operator version of a doubly stochastic matrix, right? Because in a doubly stochastic matrix, I have a matrix such that each row and each column sum to 1. And here I have something like this summing to the identity. So this is exactly what you have. It's some kind of generalization of doubly stochastic matrices where we're somehow increasing the dimension of the entries here, right? So this is it's not a coincidence. Actually, this comes from the fact that if we stop to think about it, a POVM is exactly an operator version of a probability vector. So here I draw a parallel between them. So a probability vector is just a list of non-negative real numbers that are non-negative and sum up to 1. And a doubly stochastic matrix is just this matrix, this object here, that such that each row and each column is a probability vector. As a POVM, it's something very similar to this, but for operators, right? Each entry is non-negative, but now is the positive semi-definite condition for operators instead of for real numbers. And they sum up to the identity instead of summing up to 1, but it's clearly like very similar, no? And then we can define this object here that we call doubly normalized tensor, which is exactly the analogs of this, where each row and each column is a POVM now. So if you describe both of these objects in terms of the canonical basis for matrices, what you get, we have this very standard definition of a very standard representation for matrices. But then we can see that this object we can represent as a tensor, where each of these entries appear as a coefficient for this canonical basis of the matrix. And we associate both of them via the tensor product, right? So what we want to do now is to think about Birkhoff-von Neumann theorem, which this theorem says that every doubly stochastic matrix is some convex combination of permutations, right? So this pi L are all the permutations in the given dimension of the matrix. And so actually it's an if and only if, right? So it's a doubly stochastic matrix if and only if there exists this probability vector decomposing the matrix into permutations. So in other words, we have something like this, right? This set equals to the convex whole of this set of the permutations. So the conjecture that we want to study, and actually now I already moved to this work here, which you just recently put on archive. So what we propose in this work is this conjecture. So M is a doubly normalized tensor, which is like our generalization of doubly stochastic matrices, if and only if there is a POVM Q instead of a probability vector Q, as before, such that we have this decomposition where this Q, the elements of the POVM, they serve as coefficients attached to the permutations via this tensor product, right? So another way of saying this is that the set of doubly normalized tensors is somehow the tensor convex combination of permutations, where this is very sketchy thing, very informal thing. Well, I mean this decomposition like this, okay? So it's simple to see that for n equals to 2, if the tensor has size 2, this conjecture is very easy to be proved. So because now if we have only 2 by 2 tensors, what you see is that we can define all of it via only one operator A, and the double normalization will take care of the rest. And we can always write this as something like this. So here we can see clearly the two-dimensional permutations, right? And accompanying them as coefficients, in some sense, is A and identity minus A, which form a POVM. Okay? So actually, maybe it's not that crazy, no, to have this conjecture. So actually, what we know, what we do then, is that for any n, if we have this description in terms of the permutations, so this calculation here, I won't go through it, but it's just to ensure that actually these kinds of objects, they really define doubly normalized tensors. We define tables such that we can sum the columns and the rows and find the identity. But actually, we have even more than this. We have that actually, this, after some quick calculation here, we can show that every element of this tensor, it actually can be seen as a post-processing of these QLs, where QL is the coefficients here accompanying the permutations. So what we see is that Q, the POVM formed by the coefficients, is a modern measurement for the set of rows and columns of this tensor. And the post-processing is given by this delta here. And it's a quite symmetric post-processing, because we have this relation between the rows and the column POVM elements. So on the so what we showed is that if I have the composition like this, Birkhoff-von Neumann likes the composition for my doubly normalized tensor, we conclude that the row and column POVMs are jointly measurable with a symmetric post-processing. On the other hand, now, if I assume the converse, that the rows and the columns, they admit a modern measurement and a symmetric post-processing, I can go through these lines here, and I can use the standard Birkhoff-von Neumann theorem to conclude that indeed this doubly normalized tensor admits a decomposition like this in terms of the permutations, right? Where this Q really indeed defines a valid POVM. So what we prove is that this following theorem, that let M be a doubly normalized tensor. So there exists a POVM Q serving as coefficients for the permutations in the description of this M, if and only if rows and columns are jointly measurable with symmetric post-processing. So if we take notice of the path we did to reach this conclusion, we started from joint measurability. And then we looked at modern measurements for the lamest pair of POVMs. And then we saw that these objects, they define what we call doubly normalized tensors that are generalization of doubly stochastic matrices. But then to characterize these objects, we find again joint measurability. So it's like it's a joint measurability problem inside the joint measurability problem, right? So it's a bit like Inception, right? A dream within a dream. So, but actually, this doesn't prove our initial conjecture, because our initial conjecture was to describe the set of doubly normalized tensors. Here we're only describing the ones that accept a description like this, right? So to conclude, to prove our conjecture, we need to prove that every doubly normalized tensor is jointly measurable with a symmetric post-processing. And actually what we find is that a counterexample for this. This is not true. We have this guy here, which indeed is a valid doubly normalized tensor, but its rows are not jointly measurable. So the conjecture actually is false. And what we see is that by increasing the dimension of the entries of the objects, increasing the dimension of the entries of doubly stochastic matrices, we allow for a richer structure to rise, such that these two objects, which are the natural generalizations of doubly stochastic matrices and convex combinations of permutations, there's a discrepancy here between them, okay? Nevertheless, we can still write this object M here as some combination of permutations and in which the coefficients sum to the identity, but in which not all of them are positive semi-definite. So these coefficients here, they are some kind of quasi-POVM, right? They sum to the identity, but they are not all positive semi-definite. So, okay, I'm reaching the end. So just as a summary, what we talked about. So joint measurability can be interpreted as the simplest form of measurement simulability, which means we are addressing a single simulator. There is a very natural generalization for it, which is many POVM simulability. We consider more than one simulator. And there are different forms of simulability, such as K-outcome and projective, that can be characterized in terms of joint measurability. So this is to kind of support us in our saying that actually joint measurability is very important in quantum measurement theory in terms of simulability, right? And then after that, we presented a generalization of doubly stochastic matrices arising from a joint measurability problem. And then we find the joint measurability again as a necessary condition for obtaining an operator version of Birkhoff-von Neumann's theorem. So actually I find it very nice that if you want to recover some version of this theorem for one-dimensional entries in your object, we need to impose some kind of correlation between the elements of the tensor we obtain. And this relation is given exactly in terms of joint measurability. So I think that this supports the claim that actually joint measurability also plays a role in general quantum operator theory. Right? So even if we don't talk at all about quantum mechanics, I think it's nice to look at joint measurability as a property of operators. So for future work, so just some quick ideas here. We have a very close connection between joint measurability and EPR steering, right? And now we're proposing a generalization of joint measurability. So I think it would be nice, and it could lead to nice things, to think about the connections of this generalization and some kind of generalization of EPR steering. So another thing, many of the things that we did in the first work that I presented, they resemble a resource theory, right? So we fixed the set of simulators, and non-simulability would be our resource, right? So what we saw, what we proved more or less, is that this pre and post processing that we do to the measurements, would be like the free operations in this resource theory, and in some sense, the white noise robustness would be some way of to quantify this resource, because we consider adding noise and seeing how much or the non-simulability of the measurements could take, right? So okay. So another nice thing to look at is this generalized Birkhoff-von Neumann theorem and majorization. And this because doubly stochastic matrices, they are very closely connected to majorization of real vectors, right? So it might be, and I worked a lot on this, and unfortunately I couldn't do anything. But it might be that actually this generalized theorem that we get, these generalized objects that we call doubly normalized tensors, they have something to do with some way of majorizing POVMs. Oh, okay. And just to close, it would be nice to look to further operator analogs to standard features of probability vectors, just as we did to doubly stochastic matrices. Okay. So this is a kind of map of concepts of things that I mentioned here. So we have a central point to measurability. We start talking about single POVM simulability, and then we moved in the clockwise direction. And then we talk about all of these things, and well, that was it. So you can find this result in these 3 archive papers here, and thank you for your attention.
Thank you very much. Questions?
So I'm going to bring it back to resource theories. In that resource theory of non-simulability that you point out to, do you have any intuition as to what the most resourceful measurement, or what the least simulable measurements would be?
So not really. So it surely has to be with extremality of these measurements.
With what, sorry?
Extremality.
Okay.
But that's not just it, actually. But actually, there was a paper by Teiko Heinosari and these other guys that work a lot on joint measurability. So they really extend, all of the papers basically extending this framework for measurement simulability to GPTs. So one of these results that they got is that actually there is no, resource beat for this theory. So in some sense, there is no finite set of measurements that could simulate all of the others.
Right.
So this is the closest thing that I know about.
Cool. Yeah, thanks.
Yes.
Thanks for the nice talk. Can you elaborate a bit more about this relation between the case simulability and joint measurability, with this specific restriction on the parent POVM?
Can I talk more about this?
Because you mentioned some sparsity conditions.
Yes, so actually this is a very trivial result once you get to draw the things. So the thing is that this condition, let me come back to the theorem. Here, right? So this condition says that actually when we organize the model as in this table, what we want is that in each column of it, at least n minus k elements should be null. Because then we are left to only k non-null elements in each row, in each column of this table. So this is what will give rise to the simulators, to the k outcome simulators of it. So we want a table with a lot of zeros distributed in a nice way along the rows or columns.
Okay, thanks.
Yeah.
Maybe the next speaker can start setting up.
So your generalized Birkhoff-von Neumann theorem broke down, or you found your counterexample when you increased the dimension of your operators. I'm just wondering if you can recover it if you increase the size of the tensor alongside.
What do you mean exactly? I'm not sure if I understood. So if I increase the size of the tensor here,
Yeah, the number of
increase
POVMs.
the n.
Yeah.
So what do you wish to recover if we do this?
You said you found a counterexample
Okay.
when the dimension of the operator increased.
So, okay, here. So yeah, okay, so there are different parameters taking place here, right? We can talk about the size of the tensor, which is, this case is 3. We are considering 3 POVMs in the rows and in the columns. But there is also the dimension of each operator, no? So which is, in this case, is 2.
Yeah.
But, so can you repeat the question again?
If I remember, you said that when you increase the dimension of the operator, you found a counterexample.
No, if so actually this counterexample is just increasing the number the size of the tensor. Right?
Okay.
If the tensor is size 2, we can prove easily. So
Okay.
this is already the next example, and it's already proved to have a counterexample.
Sorry, I was getting the other way around.
Okay, thank you everybody for the questions. It's time to move along, and let's thank our speaker once more.